Hello, everyone, and thank you for joining us for today's webinar, Everything a Civil Engineer Needs to Know About Hydrodynamic Separators. Before we begin today's presentation, we wanted to cover a few housekeeping items. At the bottom of your screen are multiple application engagement tools you can use. All of the engagement tools are resizable and movable, so feel free to move them around to get the most out of your desktop space. You can expand your slide area or maximize it to full screen by clicking on the arrows in the top right corner. Helpful resources are bookmarked in the related content tool. Our webinar today is scheduled to last for 1 hour and will include a question and answer period. If you have a question, please type it in the question box at any time. Please complete our brief survey for PDH credit, and at the conclusion of today's webinar, we will provide more information on how to print the certificate. Today's webinar is hosted by Marko Popovich and Taylor Barrowman. Marko Popovich is the Separation Product Manager for Contech. He has a bachelor's degree in environmental and ecological engineering from Purdue University. Marko began working for Contech in 2017 as a sales engineer. Taylor Barrowman is the Stormwater Design Engineer Team Lead. She specializes in designing treatment and detention BMPs for stormwater management. She has worked with Contech for over 3 years and graduated from the University of Louisville with a bachelor's degree in civil and environmental engineering. Now I'll turn the presentation over to Marko to get us started.
Thank you, Jill. Thank you, everyone, for joining. I'm going to get us started here with a high-level agenda for everyone, broken down into 3 major categories. Ultimately, we are going to want this to be structured around the design and the actual what it takes to get a hydrodynamic separator designed. With that, we'll start off with some basics, the background of what makes a hydrodynamic separator work and what it's actually going to target with pollutants. Then we'll move into the physical components of what makes a hydrodynamic separator work. Finally, we'll move into some external limitations, some case studies, and individual parameters that may impact how we actually design these. So starting with some of the basics here, figured we'd keep it general and then whittle down into what hydrodynamic separators actually get into. This slide shows us what typical stormwater pollutants we see. The top 3 are really what we're concerned with: total suspended solids, trash and debris, hydrocarbons, aka oil for hydrodynamic separators. But there's also the need in certain stormwater applications for nutrient and metals removal. If you've worked with Contech in the past, you may have seen Contech storm filter or Filterra for that. But for hydrodynamic separators in particular, any removal of those 2 would really be incremental, as it would be coming from the particulate bound matter there. With that, we don't really quantify any removal around those 2 components. Moving straight into hydrodynamic separator pollutants. Again, the major 3 are at the top there. When you'll hear a number of people from Contech and really in the stormwater industry talk about total suspended solids, you'll hear us refer to that as particle size distribution. So just note that that'll be somewhat interchangeable as I use those acronyms: TSS for total suspended solids and PSD for particle size distribution. The other major and really growing pollutant of concern is trash and debris. That's something that is obviously so visual for anyone that is looking at a river, a stream, a lake, ocean. Trash and debris is really the number one thing that comes to mind when you're actually looking at stormwater. With that, the hydrocarbons are something that most hydrodynamic separators have the ability to remove, but ultimately that is something that it varies by technology. Some are better than others, and really when we're talking about hydrocarbons, we're talking about floating hydrocarbons. So when it's actually sitting at the top of the water surface elevation there, it won't get emulsified oil. And again, some technologies are better than others at removing and retaining oil. So we're going to keep the focus here on total suspended solids as well as trash and debris. With that, a little more detail on the particle size distribution, total suspended solids. On the bottom of the slide, you can see not all, when we talk about sand, gravel, not all particle sizes are created equal, right? You have the very fine clays up to a more and we would call that a 50 micron. Well, clays wouldn't be 50 micron, but 50 micron would be the small end for a hydrodynamic separator, and then 250 micron would be the coarse higher end for hydrodynamic separators. Again, anything finer, that's really when we would get into a more filter-based application. And then obviously, as you would just imagine, the larger particles are much easier to remove with separator than those fine ones. Again, trying to set the tone for some basics as to what these separators actually do and the limitations around those. What actually makes these work? What are the basics behind a hydrodynamic separator? Essentially, what we're trying to do is elongate the flow path. We want the longer settling time with gravity separation. So what we try to do is implement a series of flow controls, weirs, baffles, flumes, and the goal with that is to back up water surface elevation and direct that flow path through the system to allow for the most optimum removal of those pollutants of concern. Went pretty quick through the basics here. Again, we want our focus to be around the actual components and what makes up these hydrodynamic separators. And then from there, what would really limit someone who's designing these to not be able to design it in a way they initially thought. So moving to the components here, Taylor's going to get in more detail. I'm going to give a quick high-level overview of individual components that make up a hydrodynamic separator, and then she will get into more of the specifics, the functionality, and what actually makes these work a bit more here. So with that, the really bread and butter, if you will, of the swirl mechanisms, or of the hydrodynamic separator, would be the swirl mechanisms, taking a flume, channeling it in through a cylinder, and getting a vortex path to elongate that. Similarly with splitters to get a dual vortex path. And then from there, most of these have quite a bit of internal bypass requirements. So we have the ability to not only treat water, but bypass that 10-year, that 25-year, the 50-year storm event. With that, oftentimes that's going to be dictated by the weir height, by a baffle height that you have within that structure itself. Ultimately, the goal with being able to accommodate bypass is, can we take that 50-year storm event and make sure everything's retained within our system while from those previously ran storm events? Equally important for pollutant retention would be the sump. When we design these, when we test these, the big thing with any sort of pollutant retention is going to be that outlet invert all the way down to the bottom of the structure. As you continue to accumulate sediment there, you could see turbulent forces with larger storm events and even some of the smaller ones. So the key there is ensuring that sump depth is accurate and you're not resuspending everything from those previously captured storm events. Again, something that's becoming more and more prevalent, Taylor will get more into some of the specifics on this, is trash and debris. What sort of measures are we implementing to capture that 5 millimeter requirement for trash and debris? Oftentimes you see many devices that are designed and someone's added a screen to it, and that tends to be really effective. There's a couple screen approaches that we'll talk a little bit more about here, but equally important is retaining that. When we talk about trash and debris, it's 100% capture and 100% retention. So extending a cylinder up to the top, extending a baffle up to the top slab to ensure those floatables that are sitting there, when the water dumps through, everything that's captured isn't actually dumping over the weir in a bypass event. And then some of the more quirky engineering nuances around these, inlet and outlet optimization. Oftentimes we look at testing a unit, straight pipe coming in, pipe coming out. Well, does this unit function the same when we put multiple pipes in, when we put angles in, when there's pipe drop, when we have a graded inlet? Is that flow path exactly the same as we initially intended? Will we get the same effective removal percentage and efficiency there? Last but not least, another thing that's becoming more and more prevalent in the stormwater space is maintenance. Where is the actual access point? Can they drop a vector truck in there and clean these units out? With that, I'll hand it over to Taylor to talk about some of the components, and I will talk to you all shortly. Thank you.
Yeah, thank you, Marco. So, like Marco said about different sediments and different HDS units, not all of them are the same. And that definitely comes into factor because not all of them look the same. They all come in different shapes and sizes, from a manhole to vault configurations. These treatment units can use a variety of different internal controls to promote gravity separation and prevent the resuspension of those previously separated solids. So if you look at the image here, you can see that it utilizes the flow splitter. Here, let me highlight that. This flow splitter right here to create that swirl effect. And then to settle out the TSS and store it in this sump while the water moves underneath this baffle wall and then out through the outlet pipe after leaving the outlet weir. The next image is a little bit better. So yeah, for better visualization for how these internals work, if you look here, you can see the inlet is accepting the water, and that water is channeled into the internal weir, and it's split into the two swirls, and that is how the TSS is filtered out because it extends the flow path, like we mentioned earlier. So now this isn't the same for every HDS, but generally there is an internal component that takes that influent flow and forms it into the at least one concentric swirl. And that swirl, like I said, extends the flow path and provides more time for the sedimentation. And to prevent the resuspension of previously captured materials during those peak flow events, we typically have an internal flow control where the unit is online, which means that it has both the treatment flow and peak flow rates being pushed through the system. It has to make sure that during that peak flow event, it's not losing all the water and everything that you've already treated and is being stored in your sump. So with that, let's get to some bypass flow and scour considerations. So an example of these bypass flows were that internal bypass weir, that baffle wall that you saw in the last image, as well as in this one, you can see the cylinder. So in instances where we're going to be that peak flow event, the water is still going to be pushed through the inlet flume in this one, but during that peak flow event, it's not going to lose its like all the particles that have already been settled out in the TSS that has been stored in the sump. So this unit is a little bit different than the other one, if you can't tell. This one, instead of utilizing an inlet flume, instead of utilizing the previously shown flow splitter, this one utilizes an inlet flume. So the water comes in through the inlet, it goes into this inlet flume, and then this creates the swirl inside this chamber, where it is then settled out, all that TSS is settled out and stored in this sump. So if you see here, this one also has a separation slab in order to really keep that material and all the things that are filtered out separated from the rest of the water that is then cleaned and goes downstream of our systems. So that means the sump is incredibly important. So it minimizes scour potential as well as the resuspension of those pollutants. And the depth of our sumps was designed around testing for regular inspections throughout the year. However, just like not all HDS units are the same, not all sites are the same. You're going to have a job that has 3 different HDS units on it, and none of them are going to look the same. So when you're considering what your sump is going to be looking like and what your regular inspection times are going to be, you should be thinking about what site you're using. An example of this, I'll use one of my favorite projects that's near and dear to my heart because it's from my hometown. It's in Keeneland, which is a horse park, but it's only open 2 times a year. So during those times a year, it has a crazy amount of people, and there is trash and debris that is more regular during that time than would typically be during non-open seasons. So during those times, it's really important to make sure that their maintenance team is going out there and inspecting and cleaning these units when needed. Okay, so we just spoke a little bit about bypass flow for online units, but there is additional units that you can do in offline configurations. So there may be instances where that internal bypass control is not able to handle the peak flow events by themselves. And in this case, you would use an offline configuration. And when you put your unit offline, it just has an external weir that bypasses all the other water that is above the treatment flow rate. So if you look at the image to the top here, I will use the handy dandy pen tool. So here is our bypass weir. This is designed at the hydraulic grade line for the treatment flow. So any water that's coming in here at that treatment flow or lower is going to then be directed into our system where it has our swirl and then is treated and exits our system. That internal weir there is then utilized to separate the non-treated water from the treated water. And that water exits our system and goes downstream to whatever lies next for it. But during those peak flow events, like Marko was saying, that 25-year flow, that 100-year flow or such, that's too much for this system to handle. So anything above that, we'll use a different color, is going to then go over this weir and just directly out of the system. But anything still under during that peak flow event, that is going to still be directed to our unit. So it's used and utilized in order to make sure that you have your water treated on site, as well as making sure that those internals aren't damaged during those peak flow events, because there's been some that I've seen that are massive. I think I saw one that was like 200 CFS once, which was probably one of the biggest that I've seen. But it's been also utilized when you have regulatory agencies or municipalities that require your units to be offline. So when working on a project site, you want to make sure that you are aware of what your regulations require. In Louisville, Kentucky, it is always required that all HDS units are put offline. So when I'm working there, I automatically know that I'm going to be dealing with, okay, an HDS unit. I'm going to be doing the bypass capacity calculations to find out where that hydraulic grade line is for treatment, for the treatment flow. And then I'm going to be working with that engineer to see, okay, do they need a structure beforehand as well as a structure afterwards, or can we combine it into how this configuration is, which is called a horseshoe configuration. As well, some municipalities require you to have 100% trash capture. I know that's a really big thing in California, so we want to make sure that we have screens in place to collect that trash and make sure it's not flowing downstream. So that previous example of the HDS unit also utilizes a screen to capture and retain 100% of trash, floatables, neutrally buoyant debris of 2.4 millimeters to 4.7 millimeters and larger, depending on the screen size. So we have 2 specific screen sizes that work with those. There is also 2 different types of screening. There's direct and indirect. So direct is where the forces of the water force the floatables against the screen, where the particle sizes are too large to pass. A good example of this would be like if you're making pasta and you are straining the water through the pasta, and sometimes it kind of breaks apart and there's like little bits and pieces that get like stuck on the edge of it. And sometimes you get some like water stuck behind, but for the majority, all that water gets out, but you still have some of those pieces stuck. While in indirect screening, the vertices, or oh goodness, vortexes of the water and of that swirl are forcing the floatables and solids to the center of our separation chamber. And so it is constantly cleaning and self-maintaining itself. So you don't have that little piece of pasta stuck in your screen. But you have all of that trash capture still there and really easy to be cleaned out during maintenance. Now, that's kind of the end of the components of our hydrodynamic separators, but we're going to move forward and look at different site considerations that you guys should be aware of when looking and designing of hydrodynamic separators. Before that, we are going to do a fun little poll just to kind of tell me any information that you guys are typically looking at for when you're designing your sites and your HDS units.
That's right, Taylor. Our first poll question is, what challenges have you experienced when designing and specifying hydrodynamic separators? And please click all that apply. Is it the integration with existing infrastructure, flow variation and bypass issue, sizing and design complexity, maintenance accessibility, regulatory compliance, or I have never specified an HDS unit? I'll give you some time now to mark your answers. And to submit your poll answer, please click the answer on your computer screen and then click the submit button. Looks like the answers are rolling in. Just a reminder, if you have a question, please type it in the question box, and I'll ask them at the end of this presentation. I'll share the results. It looks like 28.8% say integration with existing infrastructure, 24.8% say the flow variation and bypass issues, 31% say sizing and design complexity, 25.9% say maintenance accessibility, and 29% say regulatory compliance, and 38.6% say they have never specified an HDS unit.
Okay, well, thank you guys all for that feedback. That's really great information for us to use and to make sure that we are the best design team for your projects. So based on sizing and design complexity, that's definitely something we can touch on and we're going to touch on moving forward. And for you've never specified an HDS, maybe you will. Moving forward, what design considerations should you be thinking about when selecting your HDS units for your site? Are you thinking about sediment size, peak flow rates for bypass, trash capture requirements? All of these can help determine what the best HDS unit is for you. Do you need to have a screen? What configuration will your unit be, online or offline? Can we combine the structures by utilizing a surface inlet, where if you see this image here, you can see that there's a surface inlet, a connecting structure, the HDS unit, and then the leaving structure. It does look like this one is offline, but in an instance where you can use internal bypass, you could combine all 4 of these units to just one. And that would be saving you a lot of time for a lot of time, space, and just cost as well on your site. And then when thinking about that, okay, if we're smushing it all into one unit, you have more space, but is there enough room to invert depth? Would a shallower vault be more effective in a place where you have depth limitations? Are there horizontal limitations where a vault is not feasible for you, so you should consider multiple smaller manholes instead? There are tons of considerations for what you have and what your site is going to impact which HDS unit is right for your job, but that's why we're here. One thing to consider, and one of the biggest things that I deal with on my everyday to-day basis in my designing, is your pipe spacing and configurations. Is there an angle between the inlet and outlet? You want to ensure that there is enough space to be considering the manufacturing aspect of this. You have 2 knockouts that are very close to each other, and you might not realize that the material of your pipe is going to make that not as feasible in the design stage. So you might have to switch units or size up depending on what you're doing with your site and what is best for you. So you want to ensure that it's manufacturable. Contact makes the majority of our HDS units with precast concrete. So all of our manholes and vaults are that concrete. And our standard rule of thumb is that you want to have 6 inches from edge to edge of the pipe knockouts, just to make sure you have enough space for that rebar and we meet all loading requirements. And another consideration with the pipes is the like multiple pipes. So we can accept multiple inlets. We can have inlets coming from any angle on certain units. There's some limitations, of course, because you have to have an outlet. So for this image in the bottom, you can have an inlet in any of the blue area, and you can have an outlet in any of the orange area. So if you have multiple of them, you want to ensure that those pipe knockouts don't expose the internals. You don't want that weir, the splitter, or the inlet flume to be exposed, and you want to provide sufficient spacing for the internal components to be assembled. Along with your pipe orientation, your configuration, in respect to the internals, you want to understand if there is a significant drop between the inlet and outlet pipes. If so, this can deviate from the intended function of the HGS and can unintentionally allow influent flow to bypass. So if your outlet pipe is down here and your inlet pipe is way up here and your internals are only going to this high, but your outlet's up here, all the water coming in is just going to go whoop, right over and just bypass and not be treated. Of course, that's not always the case, but that's a good example of why we would want to make sure that you don't have too much of a drop between your inlet and outlet. And you want to make sure, because that'll increase your depth. One of the most common issues I also see, and that I personally run into, is your pipe sizes and knockout sizes. You might have a 24-inch RCP pipe, but that concrete pipe is actually 6 inches thick on either side. So if you're putting that into, say, a 4-foot manhole, you just went from, okay, a 24-inch pipe into a 4-foot manhole. It's half of it, to a 3-foot hole into a 4-foot unit. And it's like, oh goodness, that's probably too big of a knockout. You might be able to do it if it's 180 degrees from inlet to outlet, but if you have any angles in that, you might run into issues where you don't have any concrete left. So you want to be aware of that. Circling back around to what I was talking about, the depth, this is a great project example about where there was a large difference between the inlet and outlet pipes. You can see here that we have 2 inlets way up here, while our outlet is down here. And in this instance, we were actually able to increase the height of the cylinder utilizing cylinder extensions to make sure that all that water is diverted and is made into a swirl and is treated and then exits the system correctly. But in instances where you don't have the cylinder extension, if you can't have a depth that great, while this was the right solution for this project, it might have been more feasible to look at a vault structure. It might have been better for your site if we looked at an upstream structure to collect those internals and collect that water, and then at a more reasonable outlet to inlet drop, or inlet to outlet drop. Water doesn't go uphill. You can then utilize an HDS unit with just that smaller drop required. And with that, I'm going to toss it back over to Marko. Thank you guys for your time.
Thank you, Taylor. So Taylor talked a good bit about additional site considerations and what are some external parameters that may dictate how we actually design one of these. I'm going to take it a step further and kind of put my hard hat and steel toe boots on and think about what the end user with these. I've seen a number of questions asking about how are these actually put together? What do they look like when they get on site? So the big thing for us at Contact is ensuring when you are designing these units, you're keeping the whole life cycle of this in mind here. What is actually happening on that job site? How do you take it from paper, dig a hole, and put it in the ground there? Pretty obvious ones would be, is there groundwater and are there utility conflicts underneath a stormwater structure? for treatment that you're going to be putting on that site. And what sort of available area do we have? Is it really close to a building? Is it really close to landscaped area? Ultimately, does it make more sense to split flows and divert those to multiple treatment structures rather than utilizing one large one? And one that typically comes up, and it kind of goes back to some of the physical componentry in which Taylor was discussing, is how, if a site is really shallow, can we physically fit a cylinder, a flume, a weir within there? We usually need a few feet to actually have the internal components to make sure that our hydraulic grade line is where it needs to be, and we're not seeing any issues. We're not altering the flow path and the way that these units were initially designed and intended to be used. On the flip side, if these units are 20 to 25 feet deep because your storm line is 10, 15 feet underground, and you want to bring it all the way up to grade for your paved area, or even if you're putting it in a grass area, does the manufacturer actually have a structural design that still meets that HS20 loading? And is that something we need to get a custom structural design for? And then ultimately, I've said, put my hard hat and steel toe boots on. What sort of equipment's on site? Do we have a crane? What's our heaviest pick weight look like on one of these units to actually set it down in the hole right off a truck? Do we have access for a truck to get it on site and safely maneuver around there? And ultimately with that, what's above those cranes? What's above the boom on a excavator, even if that's what's setting these units? And can they properly maneuver around site without worrying about a power line hanging over the piece of equipment, or being on an airport where they have to be aware of clearance? All of those should come into mind early on in the design process. It's very difficult, as many of you know, to make these changes. Civil engineering is a very dynamic process when it comes to a job site. We're usually not the only technical experts out there. We're not the only people physically moving around. So just a few things to kind of consider while you're going early here. With that, I'm going to move to a few case studies where we had some unique design constraints and how we went about addressing those design constraints and why we ultimately decided that. So this first one, we talked a little bit about offline structures and splitting flows. So that way, when a main trunk storm line comes in, you have a good bit of flow coming through, but you only need to treat X% of that. What are we doing for treatment? On this project, it was a 3.8 million square foot warehouse with, again, a lot of moving parts, a lot of people, subcontractors, plumbers, electricians. It needed to move quickly. It needed to move safely. It was a new development that required a good bit of pre-treatment for bioretention systems because it was newly developed. And we had to kind of get creative in how we went about this. Did we want to put all of that pre-treatment through one or two units, or did it make more sense to split these flows and treat a handful of CFS, 10 CFS at a time? We're ultimately looking at 95 CFS of treated water. It's quite a bit. And there's really not many units that would ever be able to singly handle that. So what Contact did was we offered up both 8-foot and 10-foot treatment structures to accommodate this fast-moving project, because those are more readily available from a precast perspective. And ultimately, with the 8-footers, we had the opportunity to put them in a singular 12-foot structure and not split those out and have multiple structures. But it was actually more cost-effective to split those into 8-footers, saving roughly 40%, because we didn't need permitted escorted freight to ship a 12-foot manhole. We didn't need to dig really deep and actually set that 12-foot manhole, because as we mentioned before, you want that sump to be able to accommodate all of that previously captured sediment. And so the best solution was to kind of divert flow and treatment throughout the course of the site through 9 individual units. Very fast-moving project, like I said. Ultimately, the developer, the site contractor, the engineer, and everyone was very pleased with this approach, and it went very smooth. With that, we're going to go into another poll question here, and then I'll go through a couple more case studies. So I will leave you to it, Jill.
That's right. Here's our final poll question. What factor do you prioritize when selecting hydrodynamic separators for stormwater management projects? Please pick one. Is it hydraulic performance, the ease of inspection and maintenance, site-specific adaptability, cost effectiveness, or manufacturers, engineering, and regulatory support. I'll give you some time now to mark your answers. And Marko, I have a quick question to ask you while they're answering. There's been a lot of questions about offline and online structures. Can you go in and elaborate how you decide which option to go with?
The timing is impeccable on this one, actually. And before I go ahead and just start firing from the hip, as I tend to do, let's get into this next case study after this poll here, as it is a prime example of what an offline structure is. I think I might be able to use that visual aid to explain it a bit better and why we would want to put something offline.
Perfect. Well, it looks like most of the attendees have responded, so thank you very much. And I'll share the response. Looks like 23.5% say hydraulic performance, 17% say the ease of inspection and maintenance, 22% say site-specific adaptability, 25% say cost effectiveness, and 12% say the manufacturer's engineering and regulatory support.
Awesome. I'm very grateful for these responses here. As Taylor mentioned earlier, to have feedback from you all on here, it allows us to be a better partner. It allows us to support you better. So the more feedback, the better. Thank you all for those of you that filled out that survey. Moving into our next case study, and ultimately something that should really help answer some of the questions that came up regarding online and offline. I'll talk a little bit about this project, and then I'll try to use it as an example to further elaborate on offline versus online treatment. So this project was a bit of a challenge. Ultimately, the main goal was to use pre-treatment units to really keep trash and debris in particular out of a pump station. So protecting those pumps and those racks from anything that would be coming in from the stormwater. With that, the water quality treatment rate for that trash was about 30 cubic foot per second. The bypass rate was 106 CFS. So if you think about 106 cubic foot per second, I know Taylor mentioned a 201, which is mind-bogglingly large. I think back to a time where I had a hike scheduled in Zion National Park, and the West Rim Trail, we weren't able to go through it because we were supposed to cross the river, and it was 114 CFS going through that, and it ultimately would have swept us right off of our feet. The reason I'm bringing that up now with the bypass and the offline questions that have come up is think about what sort of pipe it would take to convey 100 cubic foot per second of water. It is a massive pipe. So to be able to take that, push it through to where the water can still flow through the system effectively, but we're still going to get that 30 CFS of treatment, it's a challenge. It's a huge challenge. The first solution that the developer and engineer looked at on this was actually cast in place vault. And the challenge with that was, while it was able to accommodate the large flows in the treatment, this project timeline, as was the last one, and many of these tend to be, was pretty tight. We needed to move quickly on it. They had to dewater that site. So the time that it would take and the amount of pumps it would take to dewater while they were actually pouring cast in place vault in site, it just really wasn't feasible. So ultimately they came to us and said, do you have a precast treatment option? And we took a look at it, and we found that, again, 106 CFS of bypass, significant number. Putting a large pipe to convey that into the diversion structure. So on the right-hand side, you can see this large rectangular vault here. That pipe on the bottom left, water's coming into that and a huge pipe. It's going through. The weir is allowing it to actually bypass when there's those extreme peak events. But that flow is then channeled to both of those two structures on the right, which are our CDS treatment structures, and then effectively treat and discharge that clean water there. So I hope that kind of elaborates what the key benefit and use of a offline structure would be. It's really to convey water to ensure that we're treating what is intended to be treated, and we're not pumping so much water through a treatment structure that we're experiencing resuspension and scour, as I previously discussed. Moving to our last case study here, this was another one that was a unique design challenge. The big thing here was the groundwater table. Groundwater table was high, and we were approached and ultimately looked at a large 12-foot diameter structure to handle the flow and the bypass all within a singular unit. Well, as I've said probably 3 or 4 times now, the depth associated with the sump on a manhole for this application was deep. It was 25, 30 feet deep almost. When you have groundwater table like that, that's just not feasible. So we elected to go with a vault style. This shallower vault was huge for us because it allowed the treatment and the bypass to still effectively happen within a singular structure, and it still was feasible for the contractor to put in the ground. And one of the main reasons for that was on the bottom right-hand side, you can see a crane setting that top portion of this precast. If they had that equipment on site, so it made our lives a lot easier and made the decision a lot easier to say, they're not going to have to get a separate piece of equipment to do this. We're good to go. And ultimately, I did see some questions earlier around the internal components themselves, and are those actually set, or is it expected to be installed in the field there? For this one, that aluminum swirl chamber on the top left-hand side and really on the top right-hand side as well, that came separately. We shipped out the base section, we shipped out the top section, and then we shipped out the aluminum, the hardware, the sealant, everything to actually connect that swirl chamber into the vault. That is something we as an organization try to avoid. We always try to, whether it's a vault, whether it's a manhole, to really set those internal components directly in the structure. So when it is out on site, the end user is putting it in, it sets no different than a typical stormwater structure, whether that's a diversion bypass structure or anything else. They can take it off the truck, put it in the hole, inlets labeled, outlets labeled, they can grout their pipes in, and they're good to go. In the case of this one here, where the internal components came separately, Contact has a full field consultant team where we will provide field support to assist with those internal component installation. We don't expect someone who's not worked with one of these products in the past to know exactly how everything's going to line up and that it's going to be functioning properly. We'll be out there to provide on-site support with a pre-construction meeting to ensure this is going in the way that the engineer who stamped the submittal drawing, that was approved, this is how it was built. But so then when that site is actually active and seeing stormwater coming through it, it's properly functioning and the stormwater is going through, we're getting good treatment, and we're good to go. I think this is actually lining up nicely because we've actually seen a lot of questions about maintenance here, and I'm really happy to see that. Maintenance is something that it's not enforced nearly as much as it should be. The key to the success of these units is keeping them clean. And if you're capturing debris, you're capturing sediment, you're getting all of the runoff from streets and parking lots, it's going to have to go somewhere, right? So ideally, yes, it's going into these units, but at some point you're going to need to have to maintain them. The key with maintenance, and again, this comes up early in design, is do we have easy and safe access to this? Can we physically get the 2 pictures on the right-hand side here? Can we get one of these Vector trucks next to this unit, simply pull a manhole lid, lift a hatch, drop the hose in there, jet out any internals that may have sediment or debris lying on them, and just drop the hose straight in, Vector all of the debris and sediment out of there, and dispose according to local regulations. If we're not considering that early on in design, there could be challenges, and it would make sense why no one would want to actually do maintenance as a long-term owner. You don't want to see the disruption of a landscaped area. You don't want to have overhangs and utility poles right above the boom of that Vector truck. So again, just something to consider early on design here. Maintenance is becoming more and more prevalent and enforced. More cities, more states where we're seeing the need for that. And with these maintenance cycles, it's going to vary. Taylor mentioned Keeneland there in Lexington. If you have a huge stadium with hundreds of thousands of people and there's debris and cans and plastic cups and everything running in there, probably make sense to inspect that. On the flip side, if you have something that's sitting in an isolated lot, then not seeing a whole bunch of human added elements and garbage, you might not have to do maintenance nearly as often or as frequent, because you pop the lid and you go, oh, this actually isn't that full. It's really site dependent. I wish I had an end all be all answer on maintenance for you, but again, it is so site contingent there. Another one that I believe I did see a question on as well. These are our two typical applications for hydrodynamic separators: treatment before an outfall. So before a pond, before a lake, before the ocean, before a river. And the reason that this is a hugely impactful application is maintenance. You can capture everything, sediment, debris, trash, and it stays underground. It stays in this unit. It doesn't discharge into the lake or the pond. It keeps it consolidated in one location. Whereas if you were, and when you drop that Vector truck, it's one and done. If you had to go and dredge a pond out, the cost and the time to do something like that, it can get really, really unruly. And similarly, just the aesthetic value of having trash and debris floating. Who likes to sit by the shoreline and see all of that? So to keep it contained within there, it's really impactful, and it makes the long-term life of a given area that much better. The other major application would be pre-treatment before detention. When we have underground detention systems of various material, no one wants to go, and some of these are really shallow, no one wants to have to go through and jet all of that out, inspect hundreds to thousands of feet on some of these, and then figure out, we're going to push this into one area and drop the Vector truck in there. That's a challenge. So putting a pre-treatment structure in a hydrodynamic separator upstream, it really consolidates that maintenance point and location. Again, we talked about the ease of putting that in there. With that, I am going to get us wrapped up here and move quickly into our product portfolio. So Contech, we talked about all the design parameters today, and I hope that it shed a little light to everyone here of what to look for. The expectation isn't that you're an expert on every single one of these. It's just to keep it in your mind. We have 6 separators here alone with our organization, and the reason for that is because there's different regulations coast to coast, inland. You might be talking to meet Washington Department of Environmental Ecology. You might have to meet New Jersey Department of Environmental Protection. You may have to meet trash capture requirements in California. All of these products, and the reason we have 6 of them, they do that in a different way. They have different approvals. Some of them function better than others for certain criteria. So the key takeaway from this would be, reach out to your local Contech representative. We understand what the functionality of these are, what the capability of these are, and really geographically where we see them and why we see them where we do. On that same note, if you don't want to reach out to your local rep, you don't know who your Contech rep is, you can fill out your product design worksheet here, and you don't know, oh, I don't know where my pipes can be or what sort of restrictions are going to have. That's fine. Give us the location, what sort of flow rate, if you know it needs to be online or offline, as much as you have, and we can make a recommendation based on that. And this can be found on our resource page. A number of other tools. We have design tools for underground detention and various other products, as well as technical documents to further elaborate on what our approvals look like and how these function, additional PDH articles, some of the case studies I talked about, and numerous others, as well as a list of our certified maintenance providers, people that have undergone training, are familiar with Contech's products, and can provide local folks with the ability to actually clean those out. And with that, if you don't know who your local Contech is, go ahead and punch in your area of interest on the bottom right-hand side. You can see, all you have to do is put your zip code and what you're looking at, bridge, stormwater, pipe, and we'll be able to reach out to you and provide some support. I know we have a lot of questions. Thank you all for taking the time here to hopefully learn a little bit more about hydrodynamic separators. And looks like we have about 10 minutes here to field questions. So Jill, fire away, but I don't know if we're going to get to all of them.
That's right. If you have a question, type it in the question box and I will try to get to it. Our first question is, what are the standard manhole sizes for context HDS systems?
I can get this one. So standard manhole sizes are between 4 and 10 feet, but in certain areas where there is precast availability, we can use anything from a 3 to a 12-foot unit.
Thank you, Taylor. We've been getting a lot of questions about what HDS systems are approved for the use in specific areas. How can an engineer find out what HDS systems are approved in their area?
So like Marko said, you can utilize our website. It has all of the documentations. It has all the approvals for any of our units, whether it be HDS or filter products. All of the approvals are on there, as well as standard details and anything you could use initially. And then you can also reach out to your local contact representative. Any states that I cover, I might be the one helping you with, but it's my responsibility, and it's that internal contact person's responsibility to know those and to be able to help you with it.
Thank you, Taylor. Are most of these units traffic rated?
Yes. So that is, sorry, Marko, I feel like I'm just taking over.
No, take it, fire away.
But our standard loading is HS20 or HS25. We can do custom loading if your site specifies it. Like, we've done airport loading. We've even done like a dock for a boat loading before. So if that's something that you need on top of just having that HS20 or HS25 loading, we can get that custom made for you. But again, standard is, it's highway loaded, standard, we're good.
Thank you, Taylor. I'm going to throw this one to Marko. Can a hydrodynamic separator be used for surface flow, such as at the end of a concrete swale across a parking lot?
Ooh. Read it to me one more time.
Can a hydrodynamic separator be used for surface flow, such as at the end of a concrete swale across a parking lot?
In theory, yes. It would really just depend on local regulations and how you're looking to channel that influent into the unit itself. If someone has a specific project that they're looking at, by all means, send it our way and we can take a look. It should be a pretty typical application for us, but it would just be something that we would want to take another look at based on hydraulic capacity and all that good stuff.
Thank you, Marko. Are any of your HGS systems approved for full trash capture? Yes.
So our CDS separator, one of the most common and regularly used separators really nationwide. It is rated for 100% trash capture and retention. And then our debris separating baffle box, the DSBB, that one is also rated. So it would really just depend. We typically follow the California State Water Board, and they set those trash capture. Both of those products are approved on that list. ASTM has recently worked on providing their own trash capture requirements. The level of enforcement on that, we really haven't seen it yet, but we've been seeing more and more requests for trash capture, particularly coastally, but a few sporadically through the Midwest and in the southern part of the United States here. It really just depends, but long way of saying yes, we do have 100% trash capture rating on 2 products.
Thank you, Marko. How often are HDS units used in roadway and or culvert projects?
Very often. Typically we see them more for mixed-use development, parking lots, stuff like that, but we're starting to see more DOT requirements that are more regulated on an MS4 level, where the roadway has a bunch of runoff and they want to treat it in some capacity, whether that be a highway, a state route, something like that. So we do see them pretty regularly. When it comes to culverts themselves, the biggest challenge on that end, I would say, is depending on the size of that culvert. If it's a typical 12-inch, 24-inch smaller inlet, ultimately probably some potential for us to run that through a separator and get some treatment. But if we're talking a big 96-inch arch pipe, something like that, it would really just depend on what that application is.
Thank you, Marco. Are these units pre-assembled, or is the contractor expected to field assemble the internals?
So similar to the note that I made on the shallow project that I mentioned earlier with the vault and the aluminum swirl chamber, the intent for Contact is to always install these at our precast locations. So when it gets on site, it just looks like a typical precast unit with a whole bunch of weirs, cylinders, splitters, whatever may be in it based on the given unit there. In the cases where we get something that's larger diameter, larger vault size, and we have what we would call a control section. So the piece that's actually going to contain those internal components, and that needs to be really deep and it gets to be too heavy, we will likely ship the internal components separately. But again, we'll provide field support to guide that installation and ensure that it's properly installed, it's active, it's ready to treat. It's not something that's going to be out of spec from what the engineer of record actually stamped and approved and said, hey, build it this way. If that's what they say, that's how we're going to build it.
Thank you, Marco. What is the typical sump depth?
I can take
That's
this
good.
one. Oh,
Take it.
So there isn't a typical one, but there is a standard that is set for each unit. So depending on the size, depending on which HDS unit it is, these are all factors. Again, we look at those regular maintenance intervals when we decide that originally, but this can be increased if additional is needed per your site. But again, it is to be emptied per those regular inspections and maintenance. It's a standard that is indicated on any of our standard details on our Contact website. So any HDS unit, it has from the outlet to the bottom of sump, and that is indicated for each of them.
Thank you, Taylor. And looks like we have time for one last question. What is the frequency of maintenance required for a typical hydrodynamic separator system?
Depends. It really does. Like I said, if you're going to see a big stadium, I think about some of the tailgate lots that are out there. You're probably going to want to do that on an NFL Sunday just about every weekend. But if you're in a spot that is in a more rural area and there isn't a whole bunch of runoff, and again, I'm specifically talking trash and debris there, but even gravel and sediment and sand that might be on a roadway, if there's areas where that's really, really prevalent, you're going to want to do maintenance often. We provide maintenance guides and documentation on when to do regular maintenance intervals. I would recommend a biannual inspection at the very least, maybe quarterly going into the beginning of the life cycle of that unit there. And ultimately, the inspection should be pretty easy. You pop the lid, you look, you can see what standing water is. A lot of times we'll see someone slide in a sludge judge water column that will actually show you, okay, the sediment level is this deep, or even just putting a rod in there to see, okay, this pile of sediment's almost halfway up this sump. We should be good for another 2 rainstorms, or this is pretty full. We need to get a Vector truck out here and clean it now. Again, as is with anything, Taylor mentioned it earlier, no 2 units are created the same, and that's because no 2 sites are generally created the same. We have a good understanding of what it may be, but ultimately it is it's so variable.
Well, thank you, Marco, and thank you, Taylor, and thank you everyone for participating in today's webinar. If your question was not answered, a Contact representative will reach out to you with a response. A survey will appear once we conclude the webinar. Please complete the brief short survey to get your PDH credit. A follow-up email will be sent by the end of the day that will include a link with instructions on how to download your PDH certificate. That concludes today's webinar. Thank you again for joining us and have a great day.
Thank you.